My name is Michael Austin. I'm one of the co-founders of Hidden Path Entertainment, and this talk is on procedural mesh animation with nonlinear transforms. What does that mean, you ask? Well, right at the beginning of Hidden Path, after we first formed our company, one of our first contract gigs was with Microsoft on something called XNA, if anybody still remembers that. This was back when XNA was new. It was before Unity, and it was the first time that you could actually have a powerful graphics framework, in this case DirectX with C#. And so they contracted with us to give them a really cool app that would show off the power and performance of XNA. The problem was that in the early days of XNA, it wasn't very performant. All of the messaging between managed and unmanaged code was really, really slow. And so you got like 5 draw calls if you wanted to hit 60 frames a second, just because of all of the packing of it. And it was still our problem to figure out how to show that it was really performant. So what we did is we said, okay, let's move everything that we can onto the GPU and have the GPU do all the calculations to make it look fancy, because it's still the same GPU that you have with C++, and we'll do everything there. And so what we wanted to do is have something that had like this, it was a planet full of flowers, and the flowers like fluttered in the wind, and as bombs dropped, like they all flattened and then stood back up slowly, and you could rotate it, and it had this sense of momentum and everything around it. And so what we had to figure out is how to do animating in the actual vertex shader itself. Since packing state was so expensive, any data that we packed up to send to the GPU hit our performance, and we couldn't actually use it. In case you don't know, I don't know how many people here are familiar with graphics pipelines? I hope most. Okay, awesome. The vertex shader is what actually transforms the points from world space into screen space. In general, ALU ops these days are really, really fast. A lot of actually new techniques use texture lookups in the vertex shader now, but they didn't have this back in the day. And so we're going to talk about some of the possibilities. You may say, why is this relevant, 13 years later? And the answer is that this is actually the same performance characteristics of if you do anything on Android, if you do any Switch development, or in our case, we're doing a lot of mobile VR development. And we're back into the old days where state changes are really expensive, and the GPUs are pretty fast as long as you don't have the CPU talking to them. And so all of this is kind of come full circle, and it's back and relevant to what we're working on now. And unfortunately as well, I think it's true on Switch, it's definitely true on mobile VR stuff like Quest. Texture lookups in the vertex shader are not fast. Is that animating? Yeah, okay. So what we really want is bendy trees. And the way trees are normally animated is they have a skeletal structure on them, and the skeletal structure is calculated on the CPU. And there's a lot of optimizations that have been done recently, but what you want is to look something like the right. You want it to have this kind of flowy feel where it bends back and forth, and the leaves to flutter. And the question is how can we do this without actually letting the CPU do any of the work at all? So what are some of the properties that makes good tree bending? One of them is you want it firmly planted on the ground. You want the trunk to stay vertical. You want to preserve volume, which is actually a key in a lot of distortion. And I think it's one of the reasons why there's not a lot of these techniques that I've seen shared around, is that it's actually really hard to preserve volume. You have to do a lot of math. You want to preserve distance along the trunks and branches. If you were here earlier for Squirrel's talk, when he was talking about using splines, you go, hey, splines are kind of shaped like bendy trees. Can I just move control points? And the answer is it causes stretching because they're non-uniform. And it actually means that it's less suited to this because your distances change. And our brains pick up on that and go, something is wrong. The other thing is you want the leaves to kind of sway in the wind and feel good. So I'm going to take you through some of the standard linear techniques and talk about why they're bad first. In the slides that follow, I'm going to, in general, show a math derivation and then show the shader code. This is so that if you ever go through these later, you can copy it and use it for yourself. Skew is used for a lot of grass when you have wind going through grass, where you just basically take the verts and kind of shift them back and forth. If you're only moving left and right, it's great because it preserves volume, but it doesn't preserve the orthogonality of the root of the tree, and it also causes all of your branches to get thinner and stretch in a way, like, unless you're really far away from it, this technique doesn't feel very good. In these shader fragments down below, VT will be the transform vertex, and V is the original vertex. I've done a lot of shortcuts just for the purposes of the presentation, so all of the values kind of for X and Y range between 0 and 1. But I'm giving the math so you can rederive it if you would like. Everybody's familiar with rotation. It's another of our linear transforms. And rotation's great because it preserves all your distances, it preserves your angles, it preserves your volume, and it really causes problems down at the root of the tree, and it doesn't feel like trees actually sway in the wind. I mean, everybody has had their Unity project where your trees did that at the beginning, back before they added the tree thing in. And even if you move it softly and try to pretend like there's a little bit of wind there, you can kind of get away with it, but it just doesn't fool your brain. Your brain notices that everything else is staying static. I'm also showing all of these in 2D, but it's actually a 3D model, and you can extend the math to 3D just by pulling out X and Z. Okay, so let's talk about what we really want to do. What we really want to do is somehow bend the tree along like the edge of a big circle or something like that, so that our distances are all preserved, our volume is generally conserved, and that it stays rooted at the bottom. This is the math. It's actually a pain to derive, so I put it there for you. Given a given curvature, this is the equation for it. The second term, the x cosine ky and the x sine ky, is just how you offset it from the root. So it's basically taking the derivative at any given height and letting you move, instead of left and right, it maps to a diagonal line. The problem with this, of course, if you look at it, is that when k is 0, it's not that fun. While both sine of ky over k and 1 minus cosine of ky over k are defined at 0 by the limit, when you actually put them in the shader, you get this. And if you notice it flickers and goes away. But the actual behavior is much closer to what we want, right? It's kind of cool. It wraps around the circle as you want, but this flickering gets really annoying every time it hits 0. And there's things you can kind of do to fake it by adding 0.0001, but then because it goes positive and negative, it is not really a good solution. And if you look here, this math, which may look intimidating, is really just a couple lines of shader code. This is super fast. If you do this in your game, it effectively adds no performance, or 0.5% or something to the cost of animating. Okay, so what do we do to fix that division by 0? And the answer is Taylor series. Yay. How many people know what Taylor series are? Okay, that's great. This is the right place. Taylor series is basically replacing a function by a polynomial approximation that gets better and better and better by making sure the derivatives line up with what you want. And this is a really simple Taylor expansion of the sine and cosine functions I had before. It's basically one term, and it's amazing because that one term actually gets you enough accuracy that you can bend almost 45 degrees without any distortion. So let's look at this. Yay, much better. You see it waving in the wind with my mouse. Now, if you go over 45, you do get this stretching, and it doesn't curl up into a little ball like you kind of want it to if you extend it, but you can always add extra terms to the Taylor series, and it will completely do that. So one of the things, if you notice about this, is this bends, and it bends along the edge of a wheel, if you think about it. And that's really nice, except trees don't actually bend like that. Right now, this is distributing the overall bend evenly across the entire tree. It's basically saying we're going to have constant curvature of our tree. And it would be really nice if we could instead just have a function for what the curvature we want at any given height is. So now we're going to have some more fun. So if I have a function that's theta of y, which is basically just the degree, or the radians, I guess, the angle at a given height of y, how do I mimic that? This is actually really similar to the problem that, again, to go back to Squirrel's talk, it's the same problem as going with splines. I want something that lets me take uniform steps along a spline. And that's why this problem is much harder, is because you actually have to use integration to do it. The other problem is that if theta of y is pretty much any function you pick that's not just like a linear constant, the integral down at the bottom of sine of theta of h is not going to resolve in any way that you can calculate implicitly, which is kind of what we want for a shader. But if you've been paying attention, we have a solution, which is Taylor series again. My goal is to slowly, like a lobster in hot water, add more and more math to these slides until you're feeling comfortable with it. So we have the first term is just allowing us to move along x with the derivative there, which is just basically the angle that we want. And the second term lets us integrate all the little pieces of whatever bend we have, like whether it's a wiggle or whether it's a nonlinear bend, up to the point to where we are sampling our point. Okay, so I'm going to give an example. And this is as bad as the math's going to get. It'll get cooler in a second. Yeah, that looks really, really bad. Just pretend like you don't see the bottom part. So in this case, my function is basically going to say, let's take something where the bend of an object is linearly spread out over the entire thing and skew it like a gamma curve. So like more of it's at the top end or more of it's at the bottom end, much like a gamma of like 0.5 curves downwards and a gamma of 2.2 curves upwards. In this case, it's also really good for modeling physical things. For example, if you take a fishing pole has a surface area that pretty much goes, it's a cone. You're actually holding a cone. And so the end of it has a surface area that's decreasing quadratically, which means that the gamma for it is actually cubic since it's an integration. And as you move a fishing pole, the end of it bends way, way more than the part where your hand is. For trees, it's actually the opposite thing. For trees, there's a couple things. One is the weight is what's causing the bend, is the tension on the tree. And so that tension is actually less the higher you get because it's carrying less weight. It is thicker at the bottom, which means that it requires more tension to bend, but the actual weight overcompensates for that. In addition, as a tree bends, the proportional of surface area that is into the wind is lower. And so you actually get this thing where most of the bend's low and then the tree kind of flattens out near the top. If you look on YouTube at pictures of windy trees, which maybe I'm the only person. How many people have looked on YouTube at pictures of windy trees? Yeah, okay. Then you'll notice that that's kind of the effect it has. So this math does not look very friendly. However, it's still only those two lines in the shader. Like when you actually go and implement it, it's really simple operations. So here's an example with a fishing pole. The way I have this app set up, as I move the mouse up and down, it'll change that gamma parameter, and as I move left and right, it bends. So I'll wait for the fishing pole one to come back. You'll notice with the fishing pole that the tip of it bends a lot more as I go back and forth, and this is with the gamma of 3. And it actually looks, how many people have looked on YouTube for videos of fishing poles bending? Yeah. It looks very much like this, actually. And so we've used this for also doing our fishing pole in a VR game that we're working on. For trees, I'm going to do the other thing where I set it out. So if you look, most of the bend's down low. If I did most of the bend up high, it looks really stupid. But if the bend is down low, it actually feels a lot more natural. So now I'm going to put it together. This is the shader. I'm putting up here so that it'll be in the slide deck later. The entire top half of the shader just adds noise. It's basically me calculating noise in really silly ways by using cosines of octaves of things. Often when I'm implementing this, I'll pass these parameters in from the CPU, like the overall wind and the location and things like that, since you might want that impacted dynamically. But the key of it is this bottom part where I'm basically going, adjust my angle based on the wind, add a vertical offset to mimic leaf flutter before I do the transform. So the fluttering happens and then I bend. And then do the transform, which is the same code that we saw from earlier. And here's what it looks like. And it looks a lot more natural. The tree sways back and forth. It's non-uniform curvature. The leaves flutter in the wind. You actually can turn it up and it feels really like it's a big violent storm, or turn it down and play with this, add better noise. And really all I'm doing is transforming space. There's kind of two ways you can think of all of these things. It's either I'm taking my mesh points and I'm moving them around, or I'm transforming space and sticking my mesh in it and letting the distortions of space-time hit it. And I like the second one because it means that you can not think about what points you're actually transforming and instead think about the effect you're trying to get. Here's an example of something similar to this. We're doing a mobile VR game, and you don't get any alpha, so we had to do all of the trees as cutouts. And we couldn't afford to do any animation matrices or anything for these. So this is just static geometry that has a special shader that says, look at a global parameter to see how windy it is and make it feel that windy. The tree itself is using the bending. This doesn't have the gamma curve in it. I haven't done that at this point yet. But it has the fixed curvature bending. And then the leaves, I'm just actually moving around by jittering them on the plane that's the normal plane, and sliding them around because then they don't cut through each other. They stay on top of each other. But it's a really cool effect, and more importantly, for our VR game, this cost us nothing. We went from static trees, which is usually what people fall back with, to this cool dynamic world where it feels like wind's blowing through, and it makes a really big impact in VR. Now I'm going to talk about some other effects that are less developed, but that I've used vertex shaders for in the past. And I hope that you guys can take these and get inspired by some ideas and also do cool things in the vertex shader. So one of the things, this looks pretty simple, and all this is doing a Y offset based on the square of a time variable. And our brains are really interesting. If you do something that's quadratic, like we have, I think, dedicated hardware in our brains to predicting parabolic motion. And so whenever you see anything that's parabolic, your brain will either think it's something falling or something reverse time of something falling. If you actually use constant curvature like the wheels, it always feels like it's more deliberate, like some conscious is behind positioning it because it's coming at in a non-natural angle. Now you might wonder why this is useful. How many people have here played Minecraft? Yeah. So in Minecraft, you guys know that when the chunks load, there's a hole there, and then suddenly it appears, right? And they pop into existence as your worlds load. A couple of years back, we were doing a kind of soft voxel Minecrafty game, and I wanted something that felt a little more magical for the world loading in. So this is actually doing the exact same thing as Minecraft, where we're loading the chunks away from the player over time. But by doing this kind of like coming up off of the ground, it gives this nice magical appearance feeling rather than just popping in. And it's effectively free. It's our equivalent of distance fog for loading. We had fog in at the beginning, but this was a lot more satisfying. Another thing is soft bodies. Since you can kind of create your arbitrary functions to distort space, I think that there's a lot of potential in doing soft body with just simple vertex adjustments. The key here, again, is preserving volume. That's what your brain keys on. So if you don't preserve volume, it suddenly stops looking like a wiggling Jell-O cube and instead starts just looking like a mess. And this is something that I've always wanted to play with more because you can actually parameterize even this is a simple like quadratic curve on either side, and then the height is adjusted to preserve volume. But you can parameterize it such that it can go to any angle. You can mix this with bending, so it bends and curves. The main place we use this right now is when we have objects that are like stuck to the ground and you want to pick them up. They like stretch and pull in on the side and they go pop, and then oscillate after you pull them up, and it feels a lot more physical, which again is something that we're trying to do in VR. But I really want people to play around with this more because it feels like everyone just kind of avoids soft body because they want to do it real. And you can completely fake it and have it look really good. Here's another fun one. So this is construction, and these pieces don't have to be squares or triangles. This is just me throwing something together in Unity. But the idea here is that we actually have a lot of parameters on any of our meshes to play with. We have the UV locations of the texture. We have the normal. In this case, it's like, okay, let's say to construct, we start from a position somewhere. In this case, let's say that we have a wall with the normal and this given height. Well, I can curve it out 90 degrees to the ground and have it start there and trace along that spline, right? The circle edge. Where did it go? Okay, there we go. And one of the key things too as you're doing these effects is you want to add noise to everything. Like the difference between good and just amazing is adding jitter noise, because then suddenly your brain looks for these cool patterns in it that don't exist. Here's an example in our current game of we're doing some building too. In VR, this looks amazing. And it's basically just going one material at a time, starting at a point in the center of the building, and then with some staggering based on the UVs, pulling it out into place. And when you're actually there, it feels like all of these materials are just flying out of the ground and going into the right spot. And we didn't have to do anything to get this on all of our buildings. If you're doing like a AAA game, you probably want to hand do all of these pieces, but if it's just a secondary effect in your game, you can do a whole lot without actually, without creating a per asset burden. And then the last thing that I'm going to show is this explosion one. And this still needs some work, but you get the idea. We had a game with a long time ago that involved, you had god powers and you were like throwing things at the ground like missiles and meteors. And when the impact would hit, it would put out a force wave. And when force would hit things, we would use this technique to blow the buildings into little smithereens. We'd actually shrink them as they moved away. And it was really visceral and felt really good. And it's another one of those things where with some tuning, you can actually just do this on any object. And there's a lot of different ways to do it. This one hasn't been developed. It's more for inspiration. But all we're doing, again, is just warping space and applying it to the vertices. In this case, for the shader, I'm including it again so that people who have the slides can get it. The entire top part of the shader, a lot of it is just adding noise. If you go through these slides and look at the way I do it in the shader, there's a lot of different ways I generate noise in the shader. Most of the time with cosine or sine, sometimes with U's and V's, depending on the assets. And then the next part is just solving to where the ground plane would be. And the part in the box which actually does the work is just a simple add gravity t squared. And that's what I have. If you have any questions, please come up to the mics. Something I was supposed to do at the beginning of the talk but forgot to was remind everybody to fill out your forms, and that was good. Please feel free to come up to the mic and ask a question, any questions, and I'll be happy to answer them.
Thank you for the talk. I have a question about some of your later explosion effects.
Yeah.
How do you know which verts to grab? For example, there's a group of verts that belongs to the same plant, and you want them to fly away at the same time. How do you know how to group the verts you wanted?
So it's actually nice. I think a lot of this comes out of our pipeline. I'm not super familiar with Maya and Max, but our artists have a thing where if they have a mesh, they can cut up the UVs, and it gives each one their own triangle. And the layout tools are actually fairly stochastic. So it lays out all the an individual plank will be located somewhere in the UV sheet pretty tightly coupled, and each one will be in different locations in the sheet. And it turns out that that's close enough that if you use UVs as position to make sure that your functions don't have super high frequency noise, that it will keep the plank mostly together. And since there's so many moving parts, your brain just assumes that it's all good.
Okay, thank you.
Hi, great talk. Thanks.
Thank you.
For the the jelly effect.
Yeah,
like,
soft body effect.
Soft body effect thing. You mentioned not using any actual information from the CPU because it's too costly.
Mm-hmm.
Is there like a threshold for that where like you could maybe send in a couple things?
Oh yeah, you just don't. So it depends again on the specific domain. We actually have a parameter budget for our VR game. In this case, for like soft body, you probably could send over as much as like a skinned mesh, right? Like skinned meshes send over 400, 500 variables packed into the transforms for the bones, and it's fine. And so you could do the same thing. And the big thing is that you still don't want to do it once for every vert, and you don't want to do CPU updates of the whole mesh every frame.
Sure, but that sounds like quite a lot. So you could actually get like reasonable player interaction with soft body using these.
Well, I think that for example, what I would do for this is I would say, okay, let's say that there's a stretch axis that's currently there, and there's an amount at stretch and along that axis. And now let me animate that. So maybe if you go up, you can't pull a corner and have it drop like this, but if I drop it, it's going to go and flatten, bounce, and land in the right way, because I move the axis around, and then every time it impacts, I squeeze the axis. And it turns out you can fake it, and it actually looks pretty good up. The part that's complicated is if I had it here and I wanted the player to be able to like pull out points from it.
Okay, thank you.
Yeah.
I had a question about the soft body as well.
Yeah.
Do you know like the number of verts that are in this model, for example?
In this one, you can count the number of verts if it stayed up here very long. I think I tested it like 20 by 20. But for the soft body thing, I've done it with like 5 verts tested in both directions, and it's pretty good. Especially if you have smooth normals, like you make sure that the normals are smooth.
Okay. Yeah, because I'd imagine if you only had like 8 verts, you wouldn't be able to.
It's true for all of these. Well, I mean, you could tessellate it only 8 times vertically, and it'd be more than enough. If you just had a fixed cube, it wouldn't work. The same goes for the tree too. Is when the tree bends, it would actually just be a line like an arm of a clock that moves.
Yeah.
If you don't have enough tessellation.
A small second question: do you send extra information in the verts, or generally just UV position?
It depends on the effect. There's another one I have, which is basically vines growing. And what I do is I send the center of the vine with it so that I can lerp to that position. And basically, I reduce the vine to 0 width everywhere, and then as it grows, I expand it out. So if you want something where it's like shoots it, like a flower that actually sprouts, grows, the leaves come out, and then the pop, then I sometimes will do extra information in the verts.
Yeah, makes sense. Thank you.
Yeah.
Hi, I was wondering how we can get this to work with collision.
How what?
With collision, does it work with collision?
Oh, so the nice thing about that is that even for things like the bending, well, there's a couple things. One is, in general, I leave the collision alone for trees because it's not fun for the player to not be in the collision and then have the tree bend over and collide with them. For actual placements of objects, like in this game that we're talking about here, there's objects in the tree. But because these formulas are really simple, I can calculate them on the CPU and just update it for the one object that's in the tree along with it, and it lines up perfectly.
I see. Thank you.
Yeah, no problem.
Can you go back to the gamma slides? Forward one.
One more? Okay.
So is the POW just because of the gamma? And like, if so, have you considered using something simpler like a polynomial or like an easing?
So if your gamma is integral, you can actually just multiply it out and you don't have to use the POW. What I have been told, so it's hard because I did all my optimization like back in early, like 2002, 2003 was when I went through optimization boot camp. And sine and cosine and power were very expensive functions in the shader. I've been told that almost everything is single cycle now. Like even sine and cosine is on the same order of multiply and add. I do not know if this is true, but that's what I've been told.
I think trig is, but I would be surprised if POW is. Or
yeah.
I would be impressed, I guess.
But if you know what your k is, then you should just hard code it in
yeah.
anyways. And most of the time constants work fine. Or if it's 0.5, you can change these to square roots.
Would that be constant for the whole system, or would that be uniform?
I would do it on a per object basis. Probably like you are going to have a different shader for your trees and your fishing poles.
Right.
So if you're going to do that, you can just bake it in for those individual ones. Awesome. Thank you, everybody.